Okay, so this is the foundations course, and we are recording this with Kisada. Okay, and he has seen this stuff once, sort of, but he's gonna ask all the questions that that he thinks that you guys would get stuck on. So when he asks something and it's not necessarily because he doesn't know it, it's because he thinks that you might get stuck in there. So he went through and he looked at the text, and then he kind of found out the compiled like huge list of fictions. Uh, yeah, so he's going to be asking this, and yeah, so the idea is to this one should be accessible to someone who just finished A levels. Okay, let me share the screen. So this is okay, right?
Oh, okay, sir.
Okay, now uh, let me go through some things first. The introduction to the course. So uh, so um, so this is the beginning parts are kind of accessible to uh, uh, high school students who finished, like he was entering into the like rigorous math, but it's technically possible to follow the part four. So I mean, this has four parts, and but yeah, it's gonna be like it's gonna get like very steep towards the end. But uh, I'll try to do my best to keep everything accessible. It'll be difficult, but self-contained and like yeah. Okay, so the course is foundations. Uh, Foundations of mathematics. So this is basically the proof course, that introduction to proofs course that somebody would take, like in everywhere in the world. So you take this content and then you do analysis. Okay, or like algebra or whatnot. So this has four parts. So the first part is this is done with the this is like the I mean I myself have followed this book when I was undergrad, and so let me share this with you. So the first part is we're going to go through part yeah, the text, an introduction, mathematical reasoning. This is by Peter. Like I remember when I was in first year, actually, Dr. Jampati Ratnayake, he was in fourth year, and so he found me and then he took me to the library and he gave me this book. He said like you have to go through this book, and so I was a first year student. That's how I knew about this one. So we're going to cover part one and part one, two, three. Part one, two, and three of this book. So the part one is going to be mathematical statements. And proofs. And then you have the part two, sets and functions. And the part three is numbers and counting. Okay, so actually this would give you a solid foundation to do undergraduate math, right? So without any trouble. And then and this is the part one for me, part one for the course, and then the part two. So we're gonna follow. We're gonna jump back to this book by Terence Tao. He has written a book recently. It's two books on analysis, like analysis one, analysis two, and yeah, and here is something interesting. Like you have the question like why write the book? I know there was a saying by like some mathematician, great mathematician. He was right. Like if somebody is like writing a book and you're just kind of not introducing a new approach and like just like copy pasting the same stuff or like modifying things tiny bit here and there or like adding problems or like cutting off content. If that is the case, then that person should be shot. So, and this is and sometimes I have seen actually I've seen this thing in a preface of a math book, and in there he kind of justifies the reason for writing the book. So and I think with Tao's book, the, there is a good justification. He does things starting from piano axim. So he construct the integers and we go from there. Okay. So you go through Tao so analysis text is analysis one by Tao. By Terence Tao. So this we'll go through chapter one of this book through chapter five. So basically, what he's doing, he go through the. Let me write down the topics. Okay. So I'll write down the topics, and then you'll get to kind of the nature of this course. And um, okay, so you have so he's doing the topics. There's one topic like natural numbers. So this is it does it with axioms, piano axioms, and then it does a set theory. And this is again like does it with axioms. And then from the, so now the natural numbers, then you construct the integers and rationals. Okay, and then finally you construct real numbers. Uh, Real numbers via metric, right? So metric and like what's happening in here, you have the Cauchy sequences. That's a construction in metric spaces. Okay, so the completion of metric space. And the point is like if you're doing this thing and so kind of what's happening, you're talking about rationals, and then you have a metric on rationals, and you kind of can ask the question like, is the distance function we use by subtracting two numbers and taking the absolute value, is that the only one that somehow sort of respect the structure of the integers, structure of the rationals? As it turns out, you can instead of the usual distance function, you can classify and do all the possible valuations, and you can get like something called p-adic numbers, like the p-adic norms, and you have the valuation, and then you uh, create a do the completion. And so it's nice to add that topic here. So I'll go through it. Okay, p-adic. And so there is theorem called Ostrowski's theorem. Yeah, because it doesn't look like something very. I mean, this looks like something very um, like something that's out there that doesn't happen, doesn't come in our way. But this is very important. Like for example, when you do the Riemann zeta, and there is some factorization formulas, and the explanation for those things actually boils down to things like this. So the like the generalization. So it's good to know these things, and yeah, from the like at this point. Okay, and now so this one is additional topic, but I like to get this thing done because we, Ostrowski. Uh, yeah, let's get, so now the part 3 is the other classical analysis book. That's Rodin's book. Text Rodin, uh, Rodin's book. That's um yeah, that's Rodin, like Baby Rodin, the first Rodin book. Okay, and that one, it's book one, Introduction to Mathematical Analysis. Okay, and in here he does something. He gives a construction like this is what he does. He starts with the uh, rationals, so integers and rationals. So, and in rationals, he used the ordering instead of the distance. Okay, so he introduced like the ordered fields. So the field is going to be the rationals, and you have ordering in the rational. So you're not measuring the distance between them, but you use the fact that there's a ordering, like partial ordering in there. We'll go through all that, but you're using that property to create this. This is construction by Dedekind. Dedekind. Uh, Dedekind. It's called Dedekind cuts. Uh, to construct. Okay, so somehow we're doing like two different constructions. They're like so. I'll go through this too. So somehow what's happening? Yeah, so you'll kind of cover two different approaches for the real numbers and complex numbers afterwards. And so when you do this thing and it's done, it's there. Okay, and now you think of this. So basically, so for this thing, you need these three as the requirement to go through this. Okay. So you have the rationals, and instead of defining the distance on rationals, and so you define the order, and then you get the real number. And then you have the part 4. This one is going to be kind of difficult. This is like we're trying to get to there is this undergraduate set theory book. I took a course on this from this book. It was taught by Professor Larry Morse, and yeah, so it's really nice. So the notes on set theory. Okay, and by Yanis. So this is apparently Professor Larry Morse's advisor. And so in here, we'll kind of give the kind of even more detailed foundation. So we'll go through things like cardinals and ordinals, ordinals, and things like that. And yeah, CFC axioms for sets. So this would be like introduction to like kind of more deeper foundation. So now, so kind of the picture for what's happening is this. So when you talk about foundations, you think of like something solid like this, right? And so like when I was undergrad, I was walking in here. Right? I thought that these things are very solid. Right? I build everything on top of let's say the part 1. Right? So in part 1, there are things that you take for granted. You don't ask questions about it. Okay? And so the kind of the nature of the course is going to be at one level, we would not ask certain questions. Right? So you would not ask like what is a statement. Right? So we won't define it. And at this level, we won't define what integer is. Okay, and we won't define what a set is. Okay. Okay, and then in the part 2, So we will kind of give support to these things. So you want to think of like we are not getting rid of it. So even though we are not defining it, we can like operate on top of that platform and we give support to that from the in the next layer, right? Like this. So these things get supported. Okay. And in here, like for example, in so in your in uh, yeah, for example, in like in part two, you can have questions like show that one is not equal to four, right? And so that would be so in part two, we can ask a question like show that you will get homework problems like prove that one is not equal to four, and that is like completely not accessible if we haven't have so that's even a question that you ask in the bottom level, second layer, right? So and then in the part three actually kind of at the simultaneously at the level of part two and part three are kind of the same thing. We have like we have like three core things. You'd be building natural numbers from Peano's axiom and set theory and integers and rational. From there, you branch off. You'll in rodings you have in rodings you put ordering on the rationals and you construct the different cuts and the other one you put a metric and do the other one. Okay, so the part two and part three are the kind of at the same level and you have like additional piece that's done separately. Okay, and then you have the part four. Okay, so things that are done in part four supports these things. Okay, so good. So and the like the part four is I would just show you the like there are arguments like this, there are arguments like this. I won't be able to carry out the full course, and I'm definitely not the person to do it. But I would show you like in there like you have different axioms and you construct things with like you start with five axioms and then you add one and like add the negation of that and so on, and so you create not only one set theory, you create like different universes of sets. So that is the that's what you'd be going through it somehow, like you have questions that you ask at one level and then there is a deeper question and there's a deeper one and there's a deeper one. So at one level we actually accept the question, like we accept the foundation and work on it, but in the next level when you go to the deeper level you question those foundations. So I have like a really good like I mean it is I mean uh there is a saying like in every question, like for example when you have a debate, the first thing we do with the two debate teams, they would define the terms and they would agree on the terms and then you do the debate, right? So if you're not agreeing on the terms, then it's like total mess, right? And so you have to have a common understanding, common belief, common foundation to actually discuss something upwards. But you can ask the questions about the foundation, and then you have to go down, right? For I mean, this is the best example I have, and I mean, this might get in trouble. Like but this is a good question to ask. I mean, see, like the I mean, most of us are Buddhist in Sri Lanka, so the question that uh, Siddharth Kumar, like Siddharth, he was trying to solve the question of like sansara, right? So so he didn't question. So if that's his foundation, and then you're trying to find a solution to that, and that the question that the sansara thing exists, it was like common knowledge, and everybody was operating in that setup, right? And then you can ask like, okay, wait a second, like it's before going into solving that problem, you can ask like, what are like, what are the evidence for that? That would be like going into a lower layer, right? Can we support it from something underneath, right? And yeah, this like these things go down, and you'll never get rid of the axioms, right? You'll never get rid of the axioms. You have to kind of work on something. Okay. So, and I mean, I'm doing this thing for all practical uses. So the part one, knowing part one, that was enough for me, and I learned some like part four in grad school. Uh, so and that also like in a later year. So this part four didn't actually help me through my journey, but it was like really really interesting. But yeah, so do the part one, do the part two, and in the even part one is enough to follow for the follow-up courses in Mentor. But I think now we have this book, and everybody is like following this book, Tao's and Lizzie's book, and so like a lot of people who are coming out of the in this generation, they would be familiar with this construction. That they would use the second lower layer of foundation. Okay. Any questions so far?
No, sir.
No. So, oh, the final remark, like so everybody kind of went like found these things, like the pioneers of these, like the basements of this foundation and going down and down. A lot of them went crazy, and then yeah. So it's kind of a yeah. So you have I mean, the first guy who will do those proofs. The first one who figured out the diagonal of a square. So the root two, he figured out that root two is not rational, and uh, actually the people drowned him because it was like the rational numbers were like so beautiful, and like and he came up with something. And yeah, and then there are like all sorts of stories, like if there everybody there is a tragic story. um yeah, it is hard to actually question the foundations and go down, because all the typical discussions happens upstairs. Okay, so let me finish this thing by saying this. So you had the introduction. So this is the foundations foundations of mathematics, and uh, uh, there are a bunch of courses that depends on this. Okay, so so we have analysis one, and then you have linear algebra, and uh, then there is a course statistics one. That one doesn't depend on these foundations. And there is a course abstract algebra. And there is a course that's under development that's called Geometry and Physics 1. So you'll have like geometry and physics, a sequence of like three courses. And yeah, so if you're a high school student, you finish A level and you have like 1 year, and you wanna learn more math, and you can finish this thing probably in a couple months, 2 months, because you're only going through parts 1, 2, and 3, and then you can jump in and like explore these things. And yeah, I mean these things are like uh, you can be from engineering, especially from engineering. So the in Sri Lanka you don't do this stuff, but in places like MIT or Caltech, they actually do proof-based stuff, and it's compulsory for all the engineers. And and uh, and there are, I mean, we will teach some machine learning and like applied stuff later. PD is machine learning, but all that's going to be built upon this rigorous layer. And I would like highly recommend you, especially if you're in the gap year, just like you're waiting for the universities to start, just complete these things, and it's going to be like really helpful for you. Okay, so let's I think that's the end of the uh, introduction, so let's get back into the book.